So I'm Brian Bauer. I'm the autonomy subsystem lead for the New Horizons mission. I'm here as a representative of the entire team, and I thank you for the opportunity to speak. The autonomy subsystem means that I'm in charge of the software that takes over when something goes wrong. So normally, hopefully, I don't do anything, but every so often I get real busy. So why do we want to go to Pluto, and what happened recently that caused us to want to go to Pluto? Well, recently we discovered this third zone of our solar system. So what you're looking at here are, you can see the orbits of the gas giants, and Pluto's this big dot in the bottom. And through the 90s and the 2000s, we're discovering all of these objects that are out there. And so instead of being this misfit of the classical solar system, Pluto is now part of a family. It's one of a very large number of objects that make up the Kuiper Belt. And you can see it's even more interesting because the Kuiper Belt's not flat like the rest of the solar system. It's actually quite broad. So how do you get to Pluto? You take a tiny spacecraft and you stick it on a giant rocket. So the New Horizons spacecraft is about the size of a baby grand piano. You can see some workers working on it up here. Launch mass, 478 kilograms. About 1/6 of the Rosetta spacecraft, about 1/6 of the mass of the Rosetta spacecraft. Powered by a nuclear battery, an RTG, generates the same amount of power as about 3 standard light bulbs, the 60-watt light bulbs. 7 science instruments, from cameras, spectrometers, a radio science instrument, a student-built dust counter that was built at the University of Colorado Boulder. And we also have 2 particles and plasma instruments. These 7 instruments together weighed about 30 kilograms. So a very small, very advanced instrument suite that we've put on this teeny spacecraft and launched it on a giant rocket. So this is the trajectory that we took on our way out of the solar system. We built the biggest rocket, or we contracted the biggest rocket that we could. We took this tiny spacecraft and put it on it. And speaking of throwing away your rocket, the spacecraft was going so fast when it launched that actually part of the rocket is on its way out of the solar system. It's going to leave the sun's sphere of influence entirely and go spend some time out amongst the stars. So this was actually the first spacecraft that was launched on a solar escape trajectory on its way out straight from Earth. We passed the moon in 9 hours after launch. We got to Jupiter a little over a year later. We did some observations of Jupiter just as a trial run for Pluto. We took over 700 observations of the Jupiter system, the Jovian system. And then we waited until this past July. We spent most of the time putting the spacecraft to sleep and letting it hibernate to preserve its systems and to reduce the operations cost. But since the Jupiter flyby, we've been working on this Pluto flyby, the sequence that we'll perform in the days of the Pluto flyby. And then now that we're on our way out from Pluto, we're in the process of getting approval from NASA to go forward with another flyby around New Year's 2018, 2019. This last month, we completed the burns to put the spacecraft on track to do this flyby. Now we're getting the process together, making the proposals, and hopefully we'll get to go forward with this. At 31,000 miles per hour, there are no second chances. We threw this thing out of our solar system. It spent 2 days flying by Pluto. That was the prime science. We had 2 days. And this is what our flyby looked like. Somewhat fitting, the Pluto system is tipped up on end in relation to the sun. The sun's basically out this direction. And so it is like a game of cosmic darts. The Pluto system was like a dartboard for us. And over these 2 days, as New Horizons approached Pluto, it was taking images and science in front. And then this represents about 6-7 hours of the trajectory. We flew through the Pluto system and then turned around and looked back at the other side. And 2 key observations that we made that I want to point out here is that we actually flew the spacecraft through the shadow of Pluto and Charon in order to get occultation data from the flyby. So it's an immense effort of orbital mechanics, of navigation and tracking that the team performed in order to get the spacecraft to actually get to Pluto and then fly by in such a way that we got these occultation observations. So this is what it looked like. This is the flyby. If you were on the spacecraft, this is what you would have seen. And then you'll see the occultations. There's one, and there's Sharon. So that's what we did on July 14th of this year. And if we were watching, and if the spacecraft wasn't too busy taking data, we would have seen confirmation that this happened about 4.5 hours later, because that's how long it takes light to go from the Earth to Pluto. And then it takes another 4.5 hours to go back. So this is what Pluto looked like before we flew by New Horizons. This is an image from the Hubble telescope. This is the best we had. This is what we knew Pluto looked like before we sent the spacecraft out. And this is what Pluto looks like now. It's a beautiful world. It's actually active, and I can go into some of that. It has a very varied topography, varied colors. It's very far away from an ice ball that it could have been hanging out at the edge of the solar system. It's got a heart. Everyone loves the heart. We've informally named it the Tombaugh Regio, after Clyde Tombaugh, the discoverer of Pluto. He discovered Pluto in 1930. All the names right now are informal. Our science team is busy naming everything, but it has to be approved. So everything's notional until approved. This is a closer look at the Tombaugh Regio. This is Sputnik Planum, which is the left side of the heart. We're looking at kind of the top left of the heart right now. And the left side of the heart is largely composed of these nitrogen ice flows. At the temperatures of Pluto, it varies about 20 degrees from summer to winter. It's about 20 degrees Kelvin in the summer, 20 degrees Kelvin in the winter, 40 degrees Kelvin in the summer. So it's mild. Nitrogen freezes and falls to the surface. And so you have these glaciers of nitrogen that are flowing across the surface of Pluto, and that's what makes up the Sputnik Planum, which is the left side of the Tombaugh Regio. This I'm really excited to present. The science team is in a meeting this week, and they're constantly observing and collecting and presenting new data. And this was theorized during the flyby, about a week after the flyby, and I was like, oh, I want to share this, but I couldn't. What you're looking at are mountains on the just south of what we were looking at before. And the red dots are the mountains. They're about 5 kilometers above the nitrogen surface. And they're composed of water ice, of H2O, frozen H2O. What's really cool, though, is that they're floating in the, it's believed that they are floating. It's not confirmed, but this is a belief that they're floating in the nitrogen glaciers, that the nitrogen, the sea of frozen nitrogen. So it's just really cool that we might have floating mountains on Pluto. These two are possible examples of cryovolcanism. We'd love to see cryovolcanism on Pluto. There's evidence in other places of craters on the surface that are being kind of filled in with the nitrogen. This looks a little different than that because you've got this ring built up around the outside. So it is possible that this is a cryovolcanism. There's going to be more observations to try and figure out if that's exactly what's going on here. Weird terrain on the Terminator, the snakeskin terrain. What you're looking at is kind of, it's believed to be a sublimation and deposition that's causing this odd terrain on the side of Pluto. And then this beautiful picture as we were going away. Pluto has an atmosphere for now. So what you're seeing is this tenuous atmosphere over the surface of Pluto. It actually is only present during the summer. The nitrogens melt just enough to give it an atmosphere. And then in a couple of years from now, it'll freeze and fall to the surface. It's already starting to freeze and fall to the surface. And it will be gone for another 200 years as Pluto goes back around the sun. This is cool. The spectroscopy has shown that there actually is water ice. When we saw the mountains, it has to be water ice forming these mountains. But it's actually been confirmed with the spectra. So there are sections where the surface nitrogens and methanes have been kind of washed away enough or blown away enough to actually show that there is water ice on Pluto. And here's a nice family portrait. There's a few times in our mission out that we've tried to take pictures for artistic merit. This is one of them. When we passed Jupiter, we had several, we called them Kodak moments, where people looked at our trajectory as we flew by Jupiter and said, this would be a nice picture, or this would be a pretty picture. So I don't have them in the slides. I wanted to talk about Pluto, but we have some very pretty pictures of Jupiter and its moons that were taken purely for aesthetic purposes. Charon is also interesting. It's not active, or it doesn't appear to be active. The reason we say this is because you can see a lot more cratering on the surface of Charon than you saw on the surface of Pluto. There are these crevasses, which may have been caused by kind of cooling and collapse or through other means. But it's not, it's not as smooth as Pluto. It does not really seem to have any active processes going on. One interesting feature on Charon that I'll point out is the mountain in a moat. It's right there. It's a tall mountain that's got a little moat around it. Well, pretty big moat around it. But Charon it's still an interesting place. It's just not as active as Pluto, or not active at all. One of the surprises we saw on Charon, now Pluto, the notional names are all explorers. On Charon, we're having a bit more fun. We're naming it after science fiction characters and authors. So here's the Star Wars region, the Organa crater and the Skywalker crater. And they look very similar when looked through the visible eye. But what's interesting is when you look at the spectra, the Organa crater has ammonia, and Skywalker crater does not. So it's weird that we have these two similar-looking craters with very different chemical compositions. So it's curious. We'll see. Possibly the ammonia was deposited when the crater was formed. Maybe it was revealed at the formation of the crater. Who knows? But it's just more puzzles to solve. And then finally, a look at the family. So this is the rest of the moons of Pluto. You can see their orbits and spins. It's very weird, very different. Let's see, who is it? Nix spins the opposite direction of all the others, which is very strange. They're all pretty small. You can see Charon is huge in relation to these moons, and Charon's pretty small. Pluto and Charon together kind of cover the US. So these are very tiny moons. The largest, I believe, is, well, I've got the scale, 25 miles across, something like that. So it's just a very interesting system. There's a lot more to see than we had thought we would when we first set out. And then, as I mentioned, if we get the approval, we'll be doing a flyby in another few years. And so we're already on track to do this, and here's the target. This is our fuzzy dot right now, and hopefully soon we'll be able to show you another world. Thank you.